Let's talk about section 6.1. This is the introduction to the normal distribution. This is probably one of the most important chapters when referring to any statistical and probability information that you're looking at. As we go into our normal distribution, please understand, like when I say this is probably one of the most important distributions you will learn, it does come back for many of the sections later in this course, as well as this is the most used distribution among all the different academics out there, whether it is math, or it could be science, it could be nursing, it can be psychology. This is teaching even uses a normal distribution. So this is where this is not just for a math only. Understanding this will really help you out in other disciplines when you start looking at research-based items. So let's understand what a normal distribution is first. A normal distribution is a continuous probability distribution that is completely defined by its mean and standard deviation. Now, remind yourself, I used the word there, continuous. That's really important to kind of note that this is a little different from previous distributions. Our previous distributions have been discrete, and now we are looking at continuous. So our variable has made a switch from being a discrete variable to now a continuous variable. Now, we also have our mean, which we will be using mu for, and standard deviation, which we'll be using that lowercase sigma for. Now, the graphical representation of your normal distribution is a symmetric bell-shaped curve, and it's centered about the mean of the distribution. As you look at it, it should have the mean directly in the center there. So as we can see, our mean is in the center. And then we do sometimes make references to other numbers, and normally the other numbers we like to show up on the bottom of this distribution is how many standard deviations we are away from that mean. So we're going to take the mean minus 1 standard deviation and the mean plus 1 standard deviation. This should look really familiar because we looked at something like this using the empirical rule in our previous chapters. Now, the symmetry of the curve means that if you cut the image in half, the left and right side should be mirror images of each other. Okay. However, the bell-shaped curve implies that majority of the data is in the middle. So we can still have symmetry, but not be a normal distribution. Normal distributions are going to be perfectly symmetrical, and all the data falls in the middle, as well as that mean or mode should be in the middle. Whereas something that is not normal but still symmetric, here you can see this is perfectly symmetric about this middle area here, but it's showing that all the data is on the left and the right and not directly in the middle, which this is not what we mean by a normal distribution. Anything that is normalized has this kind of all the data falls in the middle, and again, it's symmetric about the mean itself. The other thing that you kind of want to understand about a normal distribution was we talked about it being a continuous distribution, and because it is continuous, it will approach the x-axis on both ends, as you can see here, but it actually never crosses it. So if you write and draw it like this, this is actually incorrect. So it gets close, but never actually touches it. So some properties of a normal distribution is it's got to be bell-shaped. It has to be symmetric about the mean. The normal distribution is completely defined by whatever the mean and standard deviation is. The total area under the curve itself will equal 1, and the x-axis is a horizontal asymptote, meaning it gets really close to but never actually touching the x-axis. Now, because there's an infinite number of possibilities for the mean and standard deviation, this means there's an infinite number of curves. So in order to determine the probabilities for each normally distributed random variable, we have to perform separate probability calculations for each normal distribution. Now, this is not a big issue in the sense of what we're looking at, but it does sometimes worry us when we're trying to compare data. I cannot compare data where the average in the middle here is -4 compared to this one here that's at 0. So in order to do this, we do something called a standardized curve. So to be able to kind of avoid doing 4 different probabilities, I can standardize each one of the values and then just use one type of distribution. So we learned how to standardize scores back in chapter 3, and we can then reference what we call the standard normal distribution rather than computing the area under each different normal curve. Now, in order to standardize it, again, keyword here is we're standardizing it, making these all kind of resituate and become one kind of curve. A standard normal distribution, it's still normal in shape, which means it should have its bell shape and be symmetric about the mean. We are standardizing it, meaning basically we redefine the mean to be 0 and the standard deviation to be 1 if it is standardized. Okay, now a total area under the curve will still also stay as 1, and we still have the x-axis as that horizontal asymptote, meaning again it never touches. The biggest difference between a normal distribution and a standard normal distribution is a normal distribution, the mean and standard deviation can be anything. In a standard normal distribution, so in a normal distribution, it can be anything. But in standard normal, I'm standardizing it. The mean is automatically 0 and the standard deviation is 1. So let's look to standardize something. We do have to remind ourselves that all of these x values that go with different means and different standard deviations are going to have to be converted into what we call a standard score, also known as a z-score. Now that z-score, that formula we've seen previously before, and it's x minus the mean divided by all of that divided by the standard deviation. You really want to make sure that you know this formula. It's very important. It's going to come around quite often. Now, a standard score may also be called a z-score or a z-value, depending on what I'm talking about. But basically, it takes any type of normal curve and pretty much resets that to become mean is 0 and my standard deviation is 1. Okay, so let's look at an example. Given a normal distribution where the mean is 48 and the standard deviation is 5, I want to convert the x value of 45 to a z value and indicate where that z would be on a standard normal distribution. So the first part of the problem is we need to find the z-score for x equals 45. Meaning, again, take that formula, z equals x minus the mean all over the standard deviation. Now, again, x itself is my data point, that's 45. Mu is the standard, is the mean, and then we're dividing it all by the standard deviation. All of this was given in our problem ahead of time. And that tells me that my z-score, or also known as a z-value, or the standardized score, is negative 0.6. Okay, we do like to round these to 2 decimal places. It's very common to use 2 decimal place rounding when talking about a z-score. Now, to draw this, you're needing to basically mark where this would fall on a normal curve. You'll notice that it should end up in basically a very similar spot to where it was when it was just a regular x value. But because I'm standardizing it, I can now use this to compare to other standardized scores from maybe another course or whatever I am looking at comparing it to. So when you look at your regular score, the mean of 48 was in the middle. Our standard deviation was 5, so 5 above and below here. So I got 43 and 53. And 45 is that x value, kind of falls somewhere between 48 and 53. If I'm looking at a standard normal distribution, mean is 0, standard deviation is 1, so I'm going to show my 1 above and 1 below, and my negative 0.6, which is my z value, pretty much falls in the same place as it would if it was 45. But now that I'm in the z, this does allow me to compare it to other items where I know possibly they're z's. So the distribution on the left was what we have is just a normal distribution with the mean of 48. And the distribution on the right was our nice lovely standard normal, giving us that z-score of a negative 0.6. So to sum everything up, guys, what you kind of need to take away from 6.1 is that it's used for continuous data. This is what our normal distribution is actually used for. And we have a bell shape. Okay, the notation for any shorthand, it's very helpful to kind of maybe just write the big ideas down. Remind yourself that the data value is normalized with a mean and standard deviation. If you need anything that has been standard normal, so a standard normal, we do kind of switch it to a z versus an x variable. We switch to z's when we know it's standardized. It's still normally distributed, but the mean and standard deviation are given to me. Remind yourself that a standard score, also known as a z-score, pretty much just tells us how many standard deviations we are above or below the mean. If we're above, it should be a positive z-score. If we're below, it will be a negative z-score. And we just have that basic formula. This is not a new formula, but it will kind of come back and we'll make tweaks to it as we go through the course. So the basic idea is just take the data point minus the mean and take all of that and divide by the standard deviation. So I know literally how many standard deviations it is away from the mean, whether it's above or below. Okay, and that's basically the sum of all of 6.1. We will go into a lot further detail of the rest of the ideas of a normal curve.